Okay, so why don't we'll start with a clicker question here. Okay, so we'll say we will say the weight, I don't know, we'll start off with the weight of cats follow a normal distribution with mean equal, I'm going to say 8.9 pounds, and standard deviation, I don't know what I said last time, but we'll just say 1.2 pounds. Is that what I said last time also? Okay. What was the number I used last time? Because I only used the same number. Huh? 11. Okay, so now we'll do something else. All right. So I will ask, what is the probability that a cat weighs more than, we will say, 8 pounds? Okay, and let me give you some answer choices here. Okay, so your answer choices are all right, and we'll run the clicker here. Okay. All right. If you want to talk to your friends to verify your answer and discuss, you are welcome to do so. Okay. So go ahead and get your clicks in. And if you're watching online, I'm going to pause the video here. Okay, let's take a look at our answers, and that is correct. Answer choice A. So let's just see here. So here we're going to draw a curve. This is supposed to be symmetric. 8.9 goes in the middle. We're drawing a cutoff line at 8, or that's the line that we have. And over here, we want to know the area to the right. So the first thing we do is we find the z-score, and we say 8 minus 8.9 divided by the z-score of 1.2, and we get negative 0.9 divided by 1.2. I get a z-score of negative 0.75. And now I look up negative 0.75 in my z-table, which, let me find my reference tables here. So I go to z is equal to negative 0.75, and I believe the value there is 0.2266. Okay, that's the area to the left. So the area to the left is equal to 0.2266. However, the question asks more than 8 feet, so we want the area to the right. So the area to the right is 1 minus 0.2266, and we get 0.7734. And there is our answer. What is the probability that a cat weighs more than 8 pounds? I guess I should say that a randomly selected cat weighs more than 8 pounds. We get 0.7734. Okay, is this good? Great. All right, let's try another type of problem, okay? And so we have this. There are other problems where we can ask about percentile questions. Okay, and with a percentile question, we can ask something like, how heavy is a cat in the, we'll say, 95th percentile? So to be in the 95th percentile, that means this cat this cat weighs more than 95% of other cats. Okay, and so our picture will look like this. If we got a normal distribution, we want to know what is, so in the middle we put 8.9, and here now I don't know this location. What I do know is that if I shade everything over here, the area that I've shaded is equal to 0.95. Okay, and so what this requires is there are two steps. Is we find the z that gives an area equal to 0.95. And then step 2 is then convert that z back to a measurement. Okay, so what we will do is we're going to go to the table, and we're going to look for the value closest to 0.95. Okay, so we go to the table, we're going to look through all of these values. There's a bunch, but they're all in order from least to greatest, so it's not the worst thing in the world. And we try to find the value that's closest to 0.95. Okay? And so I actually find two values that are very close to 0.95, and they are equally close to 0.95. So I got 0.9495 and 0.9505. So most of the time it's not like this. Most of the time one of these values will be closer, but in this circumstance they are both 5/10,000ths away. This is in the row 1.6, and the column over here is 0.04, and the column over here is 0.05. So I'm just going to arbitrarily pick one, and I'll say 1.64, but it is, in this situation, it's okay to pick 1.65, but we will say z is equal to 1.64, okay? But 1.65 is okay because it is, just as close to 0.95. Okay. Usually, one value is closer, and use that one. But okay, so I got z is equal to 1.64. That is the value that gives me an area pretty much equal to 0.95. Okay, so now that I have z is equal to 1.64, we're going to convert this back to a measurement, x. So I've got x, z is equal to x minus mu divided by sigma. So So I will have 1.64 is equal to x minus 8.9 divided by the standard deviation of 1.2. Okay, so here we have normal 8.9, standard deviation 1.2. So I got 1.64 is x minus 8.9 divided by 1.2, and we are going to say we want to solve for x, right? So solving for x, I multiply both sides by 1.2 and I add 8.9, and I get 8.9 plus 1.2 times 1.64 is equal to x. And I punch this into my calculator, 8.9 plus 1.2 times 1.64, and I get 10.868. Okay, 10.868, 10.89, 10.9 pounds, something around there. So how heavy is a cat in the 95th percentile? We will say 10.868 pounds. That is the weight of a cat in the 95th percentile. Was this process okay? All right, let me try giving you an example here. Okay, and so we'll do another clicker question here. All right, so this time we will say SAT scores. So we'll say SAT scores for the verbal section. We'll say follow a normal distribution. With a mean of 500 and a standard deviation of 100. And we'll say, okay, what is the score of the, we'll say 75th percentile? Okay, so what is the score of the 75th percentile? And okay, so your answer choices are we got 577, 567, 570, 4, 23, 4, 33. Okay, go ahead and work on that. See if you can figure out the SAT score of someone in the 75th percentile. Okay, I'm going to go ahead and close this. Let's see. Yeah, okay. Looks like most of you guys got that. So let's take a look. So what we want is our picture looks like this. We've got 500 in the middle. We don't know what this score is, but what we do know is that if I shade everything to the left, this is going to be equal to 0.75. So go into our table. We're going to look for the closest thing to 0.75. We go through, and it looks like I've got 0.7486 and 0.7517. I would say 0.7486 is closer because it is, what, 14 10,000ths away, and this one's 17 10,000ths away. So this one's closer, and that gives me a z-score of 0.67, okay? So I got 0.7486 This is in the row 0.6 and the column 0.07. So here I've got z is equal to 0.67. So using z is equal to x minus mu over sigma, I have 0.67 is equal to x minus the mean of 500 divided by 100. Solving for x, I get 500 plus 67, 567. This is my score for x. And there we go. Yay. Okay, and it looks like most of you guys got that. So here we are for the percentile problems. Where you're given an area, you look up the area in the z table, and then you go from the z back to a score or measurement. Okay, are there any questions on the normal distribution before I move on to the next topic? You guys are good. Okay. All right. Well, thank you for speaking on behalf of the class. So we'll be our classroom representative. All right. So what we've got here, the next thing we will talk about is the binomial distribution. Okay. The binomial distribution, in contrast to the normal distribution, this is a discrete random variable. So if you'll recall, a random variable is the outcome to a random experiment. The outcome is a number. So that makes it a random variable. So the outcome is a number, and what makes it discrete is that only certain outcomes are allowed. So, for example, we can say, I will flip a coin 10 times. And the outcome I'm recording is the number of times the coin lands heads. Right? So in this case, only a whole number of heads is allowed. Okay? So the coin can only land heads a whole number of times, or yeah, heads a whole number of times. It can only land, you know, heads 5 times or 6 times or 7 times. You cannot land heads 5.3 times or 5.16 times. Contrast that to the normal distribution when we're talking about the weight of cats. When we're talking about the weight of cats, you could have a cat that weighs 10.72 pounds, another cat could weigh 10.7215, and another one could weigh 10.72164447, whatever. However, you know, if you have a super accurate scale, you can have, you know, unlimited numbers of decimals there. Okay, obviously in real life we don't have scales of that high precision, but you can imagine such a scale, and you know, as the cat breathes off air, you know, it loses weight and things like that. If, you know, every breath you breathe, you're breathing out carbon dioxide and burning up calories stored within your body, and it's through your respiration that you actually lose weight if you're busy exercising or something. But anyway, all right. So anyway, our weight is a continuous variable. Okay, normal distribution, things like that. That's a continuous variable. You know, your age on this planet is a continuous variable, except when we answer questions, we generally answer only, you know, whole numbers. How old are you? 21. You don't say I'm 21.6417 years. I mean, you could say that, but all right. Okay, so that's a discrete random variable. What makes it a binomial? Okay, so let's talk about the binomial random variable applies to certain situations. Binomial random variable, okay. Kind of the situation is you repeat the same random experiment n times. You repeat it n times, and every time you do the experiment, or each random experiment, so in our case, I flip a coin 10 times, that's what I'm doing. So in my example, we flip the coin 10 times. Coin 10 times. We're doing the same thing n times. Each random experiment has only 2 possible outcomes. That's where the bi in binomial comes from, okay? Each random experiment has only 2 possible outcomes, which we label success and failure. We're accustomed to success meaning a good thing and failure meaning a bad thing, but that is not the case here. It just means something happened or that thing did not happen. Whether it's good or bad is irrelevant. It's just something happened. And so with the coin flip, a coin flip can only have has 2 outcomes, and the 2 outcomes are heads versus not heads. Okay, now we might say not heads means tails, but thus you can turn anything into a binomial variable. So we could say I'm going to pick a person at random. Does this person have blue eyes? And our answers are yes, blue eyes, or no, not blue eyes. Okay? If we wanted to try to say, okay, how many have blue eyes and how many have green eyes and how many have brown eyes and other colors and whatever, that would no longer be binomial because you're trying to keep track of more than 2 outcomes. Okay? We can only have like blue eyes, yes or no, or brown eyes, yes or no. We cannot have multiple outcomes. We're only allowed 2. Either something is or is not. And we arbitrarily call this success versus failure. Each trial is independent of the others, meaning each trial has the same probability of success. Feel it too. Okay. Each trial has the same probability of success. So when we're talking about the coin flip, we say, each flip has probability heads equal to 0.5. So every time you flip the coin, it has a probability of landing heads 0.5, and every flip is independent of the other flips. And then the last condition in the binomial random variable is that we are interested in seeing X successes, okay, and the order does not matter. Okay. Oh, I apologize. Going back, each trial is independent of others. Each trial has the same probability of success. That probability is known as P. Okay. P is the probability of success. Okay, so we repeat a random experiment n times. Every time we do it, you have the same probability of success p, and we are interested in seeing x successes. Order does not matter. So if we say, I'm going to flip the coin 10 times, and I want to know what's the probability the coin lands head 4 times out of 10, I just want to get 4 heads out of 10 flips. I don't care if it's the first 4 flips end up heads, or if it's the last 4 that end up heads, or if it's flip 2, 3, 7, and 9 that end up heads. I just want to have 4 flips end up heads. Okay, so we are interested in just seeing x successes, whatever we decided to call a success, and the order does not matter. All right, is this okay? So let me, we'll try an example here, and then we'll work out the calculations, and then we'll kind of derive how we would go about finding the binomial distribution thing. Okay, so let's do an example. Let's say we find a special coin where the probability of landing heads is equal to 0.7. Okay, so we got this special coin. It's going to land heads with probability 0.7. Okay, we flip the coin 4 times. Okay, and we want to know what is the probability it lands heads 2 times. Okay, and what's implied here is that it lands 2 times out of 4, and the order does not matter. Okay, so it's implied 2 heads out of 4 flips, order does not matter. Okay, so let's just list this off. So what we're going to do is we're going to just kind of list all possible outcomes that satisfy this thing, we're getting 2 heads. 2 heads, 4 flips. Okay, so one possible outcome is I get heads, heads, tails, tails, yeah? All right, another possibility is I get heads, then tails, then heads, then tails. Then I can get heads, tails, tails, heads. All right, now I can get tails, heads, heads, tails, tails, heads, tails, heads, and finally tails, tails, heads, heads. Okay, and I'm pretty sure that's all of them. Okay, there are 6 arrangements, 6 possible outcomes. All right, and so let's figure out the probability for each of these arrangements. Okay, and each of these arrangements are mutually exclusive of the other, right? If the coins land heads, heads, tails, tails, it cannot have at the same time landed heads, tails, right? There's no overlap between one sequence of events and another sequence of events. They are mutually exclusive. And so I don't have to worry about subtracting off any kind of overlap. The total probability of all 6 of these arrangements is I'm just gonna add them up together. Okay, but let's find the probability of getting heads, heads, tails, tails. Okay, so first the first thing has to be heads, so I'm going to do 0.7. The second flip has to land heads, and the probability of heads is 0.7. The third flip has to land tails, and what's the probability of getting tails? 0.3, and the last flip has to be tails, and that probability is what? 0.3. I know you guys just wanted to be quiet. So the total probability, if I rearrange the terms, will be 0.7 squared times 0.3 squared. It's like, okay with everybody? Okay, and then let's do this next one. We're going to go heads, tails, heads, tails. So the probability of heads is 0.7 times the next flip, which has a probability of 0.3, that's the probability of tails, times the probability of heads, which is 0.7, times the probability of tails, 0.3. If I rearrange the terms, I will also get 0.7 squared times 0.3 squared. And just to be pedantic, we will do this third one, 0.7 times 0.3. Probability of tails again is 0.3, and the probability of heads on the last flip is 0.7. When I rearrange the terms, I get 0.7 squared times 0.3 squared. Okay, and we're going to get the same thing for all 6 arrangements. So my total probability of getting 2 heads is equal to 6. Each arrangement has the same probability of 0.7 squared times 0.3 squared. All right, is this comfortable with everybody? Yes?
Is that the only way to do it? Like listing the whole possibility?
Well, so I'm starting off this way, and then I will show you a better way, right? But just to kind of drive the point home, we'll do this one more time. Okay? I know, right? This is learning. So we had 6 possible arrangements. We did 6, and we said 0.7. That's the probability of getting heads. It's going to happen twice, and the probability of getting tails is going to happen twice. 0.32 squared. Okay, let's do the same thing. We'll say special coin, where the probability of heads is equal to 0.7. We will flip it 4 times. And I ask, what is the probability of getting 3 heads out of 4 flips? Yeah? Okay, so we'll list off all the arrangements. Okay, so I will do this for you. List the arrangements. And these are the possible arrangements. The first 3 are heads, and the last one is tails. Or heads, heads, tails, heads, heads, tails, heads, heads, and tails, heads, heads, heads. Okay, so there are 4 possible arrangements for getting 4 flips, 3 heads, 1 tail. Okay, so 4 arrangements. Okay, what is the probability of getting heads, 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 and tails? So this is going to be 0.7 times 0.7 times 0.7 times 0.3, right? So basically, it's 0.7 to the third times 0.3 to the 1. Okay, and we can see that it's going to be the same for all 4, right? So all 4 will have probability 0.7 to the third times 0.3 to the 1. Is that okay with everybody? Okay, and so my total probability is going to be 4 times 0.7 raised to the third times 0.3 raised to the 1. That's going to be my probability of getting 4 heads out of, I'm sorry, 3 heads out of 4 flips. All right, so this is what I have. Let me kind of generalize this a tiny bit, okay? And so we have, the probability for getting X successes is equal. So what we have is the number of arrangements of x successes out of n flips, or n trials, I should say. Okay, so we have the number of arrangements times what I want is the probability of success and I would raise this to what power? I would raise this to the x, right? I need x successes, the number of successes. So probability of successes raised to the number of successes multiplied by the probability of a failure, right? Probability of failure, which is getting our tails, probability of failure, and I raise this to what power? The number of failures, okay? Which, if we want to replace with symbols, okay, I'm going to just say, I'll still leave this as number of arrangements times probability of success is p raised to the, I should get rid of the letter x here so you don't get confused here, p raised to the x power, number of arrangements, p raised to the x power, right? Probability of success raised to the number of successes. And what's the probability of failure? 1 minus p. And what is the number of failures? N minus x, right? If we have n total trials, there has to be x successes and n minus x failures. Okay, so that's what we have. So we've got number of arrangements times p raised to the x times 1 minus p raised to the n minus x. So this is the probability of getting x. The probability of getting x successes is the number of arrangements times p to the x times 1 minus p to the n minus x. Okay, so how do we get this number of arrangements? That is our last slide, okay? And this is, so the number of arrangements, this comes from combinatorics. And basically, the number of arrangements is equal we write this, nx, this is also written as n choose x, n choose x. And the formula for this is n factorial divided by x factorial times n minus x factorial. Now I don't expect you to remember this because there's probably a button on your calculator that does this for you. Okay, so look on your calculator, look for something that looks like NCR. Okay, you want to look for an NCR button. On my calculator, it's over the division key. Okay, and so you can do something like 10 and then second division, 10 choose 5, and this says there are 252 arrangements for 10 flips and having 5 heads or something like that. If you have a TI, you might have a math button or a PRB button for a probability button, okay, because this is probably when we use them. Or you might have to hit math and then go through the menus to find PRB. And then once you find PRB, you might find NCR somewhere in there, okay? And again, if you do 10, choose 5, you should get 252. This is the number 10, or I'm sorry, it'll be 10 NCR, NCR 5, okay? 10 NCR 5 should give you 252. If you can't find this on your calculator or you don't know how to use your calculator, come see me. I'll be happy to try to show you and explain this to you. And I guess everybody's packing up, so we'll just we'll call it a day here. Have a great weekend, you guys. We'll see you guys on Monday.